Today we talk about interval. Interval, first we start from this definition. Definition of interval. Definition of interval. We write this definition now. We know about that a subset J subset of R, a subset J subset of R is an interval, is an interval if and only if for every xy belongs to J and for every z such that x less than z less than y, it follows that z belongs to J. Okay, that means a subset J subset of R is an interval if and only if for every xy belongs to J and for every z such that x less than z less than y, it follows that z belongs to J. Okay, now we're going to further portion. We develop one proposition and we prove it. We first write this proposition. Any subset J subset of R, any subset J subset of R is an interval if and only if it is of the form open AB, closed AB and closed A, open B, open A, closed B and minus infinity beta alpha infinity, and here closed alpha infinity minus infinity beta closed or R, and here A less than equal to B. Note that the empty set is an interval. Here A less than equal to B and open A infinity implies that those x such that x greater than A. So we talk about this proposition. Any subset J subset of R is an interval. J is an interval if and only if it is of the form open AB, closed AB, half closed A, open B, open A, closed B, open minus infinity, closed B, open B, open alpha, open infinity, closed alpha, open infinity, open minus infinity, closed beta or R. Here A less than equal to B and A infinity equal to x such that x greater than A. Okay, so today we prove this. Now we erase all this portion properly, then we prove this proposition. proof. Now if J is one of the types specified in the proposition, then it is clearly an interval. If J if J is one of the types, if J is one of the types, J is one of the types specified in the proposition, then it is clearly an interval. It is clearly an interval. Okay, so we need to prove the converse. Now converse. Let us break into two cases. Now let us break into two cases. First one is J is bounded. First one. And second one is J is unbounded. Case 1. First case here. If J equal to phi, then nothing to prove. So we assume that J is non-empty. So we assume that J not equal to phi. Now start with this. Let A equal to infimum of J and B equal to supremum of J. We claim that open AB subset of J subset of closed A closed B. For if A less than X less than B, then X greater than A, and since A is the greatest lower bound, then there exists a C such that C belongs to J such that C less than X. And similarly using the fact B equal to supremum of J and X less than B, we find that there exists D belongs to Z such that X less than D. Okay, x less than d. Thus what we get, we erase this properly. We erase this properly. Then what we get? We get what we get? We get thus we have CD belongs to J such that C less than X less than D. C less than X less than D. Okay. Now since J is an interval, it follows that X belongs to J. It follows that X belongs to J. Since X belongs to AB, since X belongs to open AB is arbitrary, we now show that we have shown that AB subset of J. Okay. By this definition, by definition of AB, if Z belongs to J, then A less than equal to Z less than equal to B. Hence J subset of AB. Now depending upon whether or not, whether or not AB belongs to J, whether or not AB belongs to J, we find that J must be one among open AB, open A, closed B, closed A, open B, and closed AB. Okay, we are now sure that the reader should be able to supply the proof of case 2. Now we study case 2 now. Case 2, we say about that since J is unbounded, what we do? We do so simply. There are three possibilities. First one, it is bounded above but not bounded below, Second one is it is bounded below but not bounded above. and third one is neither bounded above nor bounded below. Okay, now erase all these portions. Now we start with next part, case 2, and now erase completely. Then we start this portion. This portion is too easy. We develop this portion now. So what we done? We done simply first, let B belongs to supremum of J. Let B equal to supremum of J. Then we claim that minus infinity B subset of J subset of minus infinity B. Okay, let X belongs to minus infinity B open. Then J is not bounded below. Then J is not bounded below. So what we do? X cannot be a lower bound for J. X cannot be a lower bound for J. Lower bound for J. Therefore, there exists C belongs to J. Therefore, there exists C belongs to J such that C less than X. Okay, since X less than B, since X less than B and B is the least upper bound for J, and B is the least upper bound for J, least upper bound for J, then there exists D belongs to J such that C less than X less than D. Okay, so X belongs to J. Now we proved all these portions. Which one? A subset J subset of R is an interval if and only if it is of the form open AB, closed AB, closed A, open B, open A, closed B, open minus infinity B, open alpha infinity, closed alpha, open infinity, open minus infinity B or R. Now we erase these portions properly. Now we start with this. Now let's start with this portion. We have to show that one question is important question. We mark it. A non-empty subset of R. A non-empty subset of R is an interval. Subset of R is an interval. A non-empty subset of R is an interval if and only if it is convex. If and only if it is convex. Okay, we prove it. It is too easy. but we have to prove it now. Okay, so what we do this one. Let J be an interval. Let J be an interval. Okay, then let A B belongs to J. Let A B belongs to J. Assume that A less than B. Assume that A less than B. So then closed AB equal to X belongs to R such that A less than B. Subset of J. Subset of J, since J is an interval. Since J is an interval. So what we done? We done if x equal to 1 minus t a plus t b for t belongs to 0 1, then a equal to 1 minus t a plus t a less than equal to x less than equal to 1 minus t b plus t b equal to b. Hence x belongs to AB. That means therefore x belongs to J. Therefore x belongs to J. And conversely, that means if J is an interval, that means a subset of R is an interval, a subset J contain J is a subset of R is an interval, then we prove that x belongs to J. That means and x equal to this one belongs to the J. That means J is convex. J is convex. Now in converse way, if J is convex, then conversely we proved it. If J is convex, J be convex, then AB belongs to J, implies that 1 minus TA plus TB belongs to J. Okay, then we construct x equal to 1 minus TA plus TB. B belongs to J. So we start that 1 minus TA plus TA equal to A less than equal to 1 minus TA plus TB equal to x less than equal to 1 minus TB plus TB equal to B. Okay, then we find that x belongs to AB. If convex, then in this way x belongs to AB. Then obviously x belongs to x be convex. So x is in this way we write it. Then x belongs to AB also. So J become and J, if J be convex, then every element of J, any two element of J, this contains another element. That means A less than x less than B. This implies that A less than x less than B. So this, by definition of interval, J be an interval. J be an interval by definition. So this proof is done here. Today we stop here.